Okay, coming back to this later half of this lecture, we will continue with the study of ideals. Now we should construct new ideals from the given ideals. So this is comes under the subsection called operations on ideals. On ideals. So first is, if I have two ideals A and B, then I can define their sum. And how do I define the sum? Obviously what you can do is, you take elements from here and elements from here and add them, A plus B, as A varies in A and B varies in B. And now you check that this is an ideal. This is obvious because what you can check is, it is a subgroup and it is closed under arbitrary multiplication by an element in the ring A. So here our ring is fixed, A is a ring and we are considering ideals in that ring. So sometimes the set of ideals in A, I will denote by this IA, script IA. So this is Gothic A, says that A is ideal in A. And definitely this is a non-empty set, because 0 belongs here, ideal 0 belongs here, and also the unit ideal belongs there. So there are at least two elements there. And this set, on this set I have defined addition by using the addition in the original ring. If I have two ideals, then you take their sum or some elements from those ideals and check that this is an ideal. This is called a sum ideal, sum of A and B. And you see, you have observed that, like earlier, it may be sometimes better to define this is the smallest ideal which contain both. So this is the smallest, A plus B is the smallest ideal containing both A and B. And see, this observation will allow us to define, if I have an arbitrary family of ideals, AI, I in I, family of ideals, then we can define this sum I in I, AI. Remember, we are not taking infinite sums. This is just a notation for the smallest ideal which contain all of the ideals. And definitely there is one ideal which contain all of them, namely the unit ideal A. So it makes sense. So this was the first operation on the ideal, the sum operation. So this was 1, 2. This was a bit easier, but now let us take another one, the intersection. So intersection of ideals. So if I have two ideal A and B, then I look at the intersection A intersection B and check that this is also an ideal in A. This is obvious because the intersection of subgroups is a subgroup, you would have learned in a group theory, and also it is closed under arbitrary multiplication by an element from the ring, because both satisfy that property. And similarly, we can actually define these for arbitrary intersection, arbitrary family. If I have a family of ideals AI, then intersection AI, this also is an ideal in A. Now it is, let me just pause here and look at example. So in the ring A equal to Z, let us see what happens. So we know that all ideals in the ring Z, they are principal and they are unique, the unique generator is the natural number. So A is Zn, all Z multiples of this n, and B is all Z multiples of m, where these n and m are natural numbers. If I have take two such ideals, what will be A plus B? A plus B is in this notation all multiples of n plus all multiples of m. And what is this? These are we know this again has to be principal, because we know every ideal in the ring Z is principal. So this should be also principal. And what will be the unique generator? That is precisely the GCD of n and m. This I would say check this. That is clear, because how do you write GCD? How do you compute GCD of n and m? GCD of n and m is a combination, Z linear combination of n and m. So that is A times n plus B times m. So when you multiply this and so on. So please check this. But this is very special, true in case of Z. It is not true in arbitrary ring, because this GCD does not make sense in the arbitrary rings. And what will be the multiplication or intersection? Intersection first. This will be Zn intersection Zm, and again now you might have guessed this is nothing but ideal generated by the LCM of n and m. Again check this. This is not so difficult. This is the school arithmetic gets converted into this language of rings and ideals on divisibility and so on. Alright, so this was one. Now intersection, now the next definition about operations on ideals is, that is the third one, that is the product. You may have noticed that whatever we have studied in arithmetic in the school, now we are trying to study that arithmetic for ideals. But obviously the ring Z has a special property, it has a Euclidean algorithm, etc. Arbitrary ring may not have that. So whatever machinery we have for Z, that may not be available for arbitrary ring. So things will not go as it goes for the ring Z. Okay, so suppose again for two ideals, if A and B are two ideals in A, the ring A, what should be the product ideal? Obviously it suggests that all products should be there, but then the difficulty is that it may not form in subgroup. So then the right way to say is, take this is the ideal in A generated by all products A times B, where A is in A and B A is in the Gothic A. and B is in Gothic B. So, take the ideal generated by that. So, in our notation it will be like this. So, this is same thing as summation A times AB, and the summation is running over AB in A cross B. This is the formal notation. So, these are all principal ideals generated by A, B, where A is in A and B is in B, and take. So, this means what? This we know, this is finite sums, the set of all finite sums, finite A linear sums like this, J in J, AJ. Now, I need some other CJ, AJ, BJ, where CJs are elements in the ring A, AJs are in the ideal A, and BJs are in the ideal B. So, that is the product, and again nothing special about 2, but now we can go only for the finitely many, because product of, if you are finite arbitrary family, then product will not make sense. So, similarly I will just say, similarly if A1 to AN are ideals, in A, then the product A1 times A2 times AN, this is defined. And what is obvious is, so I forgot to mention, for two ideals A and B, what is the relation between A times B, A intersection B? See, this is generated by the products, and each product is in A as well as in B. Therefore, each generator of this ideal is contained in this ideal, and therefore, this ideal is one of the ideal which contains all the generators here. Therefore, this inclusion. So, again check that each generator, it is not very good to write like this, each generator generating set AB, A in A, B in B, this is a generating set of the product ideal is contained in A intersection B, and therefore, this inclusion. Now, one more operation which I want to introduce now only, because later on we may not have appropriate place. So, if I have two ideals A and B, this definition which I am making, it is analog to the division, it is analog. We cannot write A divides B, but this is similar to that. So, for ideals, two ideals in A, I am going to define a colon ideal, A colon B. This is the notation, A colon B. This is equal to all those elements lambda in the ring A such that lambda times B is contained in A. So, what does this mean? This means for any B in B, lambda times B is an element in the ring A, element in the ideal A for every B in B. Okay, so this is called a colon ideal or ideal quotient. Ideal quotient. This is the ideal quotient. Alright, and obviously this definition is so restrictive that we cannot define it for arbitrary ideals, arbitrary many ideals. So we will special case where it will be very interesting is when the ideal A is 0. Then what is this? This is 0 colon B means what? Let us write down this definition. This means all those elements, let me not use the letter lambda, but let me use the letter R. R in A such that R times B is contained in A, but A is 0. So, R times B is 0. That means what? That means these are all R elements A in A such that R times any B is 0 for every B in B. This for every. This might remind you, this is precisely the definition of, so when 0 colon B, therefore 0 colon B is nothing but annihilator of B. What is the annihilator of B? That is all those elements in the ring which kills B. See this, it annihilates. So, this is called annihilator of B. Later, yeah, this is O of B. All right. So, that is all about the operations about the ideal. I will come back to this again, improve this with more observations and examples. But right now also I want to remind that whenever I have a ring homomorphism, if A to B is a ring homomorphism, then kernel of phi, which is by definition, I will write in the notation kernel phi, this is by definition all those elements A in A such that phi of A is 0, this is a subset of A, is an ideal in A. And note that this is kernel is always a proper ideal. Kernel of phi is not equal to A, because it never contains a unit. If you have a unit, so if I have a unit U in A, then I just have to check that phi of U is not 0. That is because, so then this U will not be, U will be an element here, which U will not be here. And why that? Because I know phi of 1 is 1. This is 1A and this is 1B. So, if I multiply, it's a U is a unit, therefore, there exists a V in A with UV equal to 1 But when you apply phi to this, you get phi of u v equal to 1, which is phi of u phi of v. So, therefore, we can conclude phi of u is also unit in B now. So, ring homomorphism maps units to units. So, that means this phi will induces a group homomorphism on the unit groups. So, that means we have a map which is I will denote by phi cross, which is a map from A cross to B cross, and this is a group homomorphism. With respect to the multiplication in A and with respect to the multiplication in B. All right. Now, kernel, we have noted kernel gives a proper ideal. So, in particular if A were a field, then the kernel is not the whole field K, therefore, we have only chance that it is 0. So, therefore, I should note that if phi is a map from a field to somewhere, B is arbitrary and K is a field, this is a field. If this is a ring homomorphism, then kernel of phi is 0, that means that is the map phi is injective. So, more generally I should have noted if I have a ring homomorphism from A to B, ring homomorphism, then phi is injective if and only if kernel of phi is the ideal 0. So, let us write a short proof. This way first. Suppose phi is injective, then I want to prove the kernel phi is 0. So, let some element A be in the kernel phi, but that is equivalent to saying phi of A is 0. But phi is injective. So, and also we know it is a ring homomorphism. So, 0 will go to 0, 0 goes to 0. That is again very easy to prove. If more generally if you have a group homomorphism, then the identity in a group should go to identity in the other group. So, but this 0 is phi of 0, but injective, phi is injective. So, that will imply A equal to 0. So, we have proved this way. Conversely, suppose kernel of phi is 0 and suppose the two elements give the same image under phi, then I want to prove A equal to B for injectivity, but this is equivalent to saying phi of A minus phi B is 0, but this is same thing as because it is a ring homomorphism, addition etc. This phi of A minus B, this is 0, but that is equivalent to saying A minus B is in the kernel phi, that is equivalent to saying this is 0. So, A equal to B. So, that is one way to test. So, in this case then A will be a subring of B. Okay. So, now we have seen the kernel is an ideal in general Conversely, we will now check that if I have any ideal, then it is kernel of some ring homomorphism. Now, I am trying to check conversely. That means what I am trying to check? I am trying to check, suppose we have a ring A is a ring and A is an ideal in A. Then I want to define a ring homomorphism from A to some other ring. So, let me write this ring homomorphism special name, let me write this name as pi. So, we are looking for some other ring B and a ring homomorphism with kernel of pi is precisely A. So, we want to construct pi, we want to construct a ring B, we want to construct a ring homomorphism phi such that kernel of pi is precisely A. And this is precisely called construction of residue class rings. Class ring of A by an ideal Gothi K. This is also called quotient ring. Ring of A by an ideal, this one. So, this is similar, this you will already have seen the construction in groups. If you have a group and you have a arbitrary subgroup will not work, because something has to be well defined and then you will need a normal condition there. But we have an advantage here, our rings are commutative. So, that will help us to go quickly. So, this ring, what am I doing? So, remember this, the Gothi K ideal A under addition, this is a subgroup of A plus. So, this is a group, abelian group, and this is a subgroup. Therefore, this quotient group makes sense. This is a quotient group. So, what are the elements? The elements are the cosets. So, A plus A. Plus A. This is a coset. And then you look at these cosets. So, as A varies in A, but obviously two cosets can be equal for two different elements. So, and what is the coset? A plus A. A plus A by definition, this is the small a plus arbitrary element of A. So, that is plus A prime, let me write it, A prime in A. This is a coset, additive coset of the ideal A by this element A. And you know then how do we define a group structure here? We have A plus A, that is one coset, another coset B plus A, then you define this as A plus B coset of this Gothi K by the sum A plus B. And now we will have to check that this definition is well defined. That means this definition does not depend on the representative of A and representative of B. So, I will only write down the problem and I will leave it for you to check this is correct. So, if that means if A plus A equal to A prime plus A and B plus A equal to B prime plus A, that means the cosets, these representatives are the coset representatives of these cosets, they may be different, two cosets are equal, then A plus B plus A is also same thing as A prime plus B prime plus A. And now how do you prove? Once you write down this, what is this, what does this mean, then it will be clear. So, this is equivalent to saying A minus A prime belongs to A, and this is equivalent to saying B minus B prime belongs to A, and this is similarly this is equivalent to saying A plus B minus A prime plus B prime belongs to A. This is what we want to check. This is what we want to check. That means equivalent to check. We want to check this, but we have given this. So when you add it, you get this. So that is obvious. So therefore, this operation is well defined. Now I want to define the multiplication, and that gives a clue how to define a multiplication also. So if I have one coset A plus A, another is B plus A, then multiply them by just writing AB plus A, and now again we have to check it is well defined. I will just say check. So therefore, and with these two definitions, this quotient group will become, with this multiplication, this will become a ring that we have to check. Again check. That means it's abelian group, it is monoid, and there is an identity element. And what is the identity element? Identity element is precisely 1 plus A. This is the identity element. This is one of the quotient ring. All right, and therefore, and also the pi map is obvious now. That is A going to A by A. This map is defined simply an element A goes to the element the coset by A. And now this is the way we have defined, this is a ring homomorphism. With kernel of pi equal to you see what, all those elements A in A such that A plus A is 0, but which is equivalent to saying A belongs to the ideal A. So this kernel is precisely the ideal A. So what we have checked is, given an ideal A, there is a ring homomorphism from A to some other ring. This is not the only ring where A will be the kernel, but there may be some other also. But this is a very natural construction. This ring A is called a residue class ring. A ring of A by the ideal A. For example, if you take A to be Z and ideal A to be the principal ideal generated by this n natural number, then Z, this quotient ring, is nothing but Z modulo n. This, so I will come back to some more. The last proposition here is about, this is called usually the fundamental homomorphism theorem, fundamental theorem of homomorphisms. So what does it say? So this theorem, this is fundamental theorem of homomorphisms. This is usually one writes in the first books on the rings, but I must mention this is actually proved by Noether. These are also called Noether's theorem. Okay, so what is it? So let phi from A to B be a ring homomorphism then there exists okay, let me be a little bit more general. Then if it's a ring homomorphism with and A is an ideal in with the ideal A is contained in the kernel of phi. So I should have said in the beginning let and A in A ideal in A with ideal A is contained in the kernel phi. Then there exists a unique ring homomorphism from, so A is here, this A quotient ring A by A is here and this B is here, this is our given phi, this from the ring A and from the ideal A we have this residue class ring and this pi ring homomorphism. There exists a map from this that is denoted by phi bar. There exists a unique homomorphism phi bar from the quotient ring A by A to B such that this diagram is commutative. That is, when I say this diagram is commutative, that means you see usually there will be one point where you can go this way and then from this point you can go this second way. So this should be same such that phi equal to, so that is this equal to pi followed by phi bar, pi compose phi bar. So proof, let us write quick proof. Proof. I want to define what is, we want to define this. We want to define phi bar. That means I want to define what is phi bar of the coset. But then this commutativity demand will dictate you what to do. This A plus this coset is here, this is a coset of this A and this A will go somewhere here, phi B, and we want this equality. So we are forced, not B, sorry A. This is A and we can define this. Now as usual we have to check that this definition is well defined. Simply whenever we are defining a map from a quotient set to somewhere, you always have to check that map is well defined. And what does that mean? That means if I have another coset A plus A and A prime plus A, these two cosets are equal, then I have to check this side is equal. Then this map will be well defined and then the commutativity will be obvious because that is how we are forced. But what does this mean? This means the difference A minus A prime is in A, and what does this mean? This means A minus A prime belong to the kernel phi, because when you shift to this and then use the ring homomorphism, so it is in the kernel phi. And what is the given relation between this and the kernel? that this is contained in the kernel, that is given. See, this is given to us, this is given to us. So, this is given to us, and then that will mean this, and that is equivalent to say this. So, we have checked this. So, well definedness is checked, and ring homomorphism we have to check, it is a ring homomorphism, that is again I leave it to you, and commutativity is forced, so that it is clear. So, I will just derive one corollary from this. So, because one corollary I will deduce. So, when is this phi bar injective? Phi bar is injective if and only if A is precisely the kernel, and phi bar is surjective if and only if phi is surjective. This is again I would say obvious, you check this, check these equivalences, and then therefore, I can state the corollary. So, corollary, okay. Let phi be a ring homomorphism from A to B, be a surjective ring homomorphism, then there exists, then phi induces a unique isomorphism of rings A mod kernel of phi to B, such that the diagram A here, B here, phi, this A by kernel phi, this is a residue class ring by this ideal kernel phi, this is our pi, such that this map, this is phi bar, and this is an isomorphism. Isomorphism of ring means it is a bijective ring homomorphism, or equivalently there exists a ring homomorphism in the other direction, so that both composites are identity. So, this is just this observation, because phi is surjective given here, therefore, this map phi bar is surjective from the corollary. I am applying the theorem to the ideal A equal to the kernel phi, and then first will tell you this phi bar is injective, and second observation will tell you this phi bar is surjective, therefore, it is bijective, therefore, this is a ring isomorphism. So, I will now stop here, and in the next lecture now I will have to digress little bit about special kind of ideals, namely prime ideals and maximal ideals, and after that we will also go little bit basics about the modules. With this I will stop here, and we shall continue it in the next lecture. Thank you.